This is part 2 on solving trig equations. And basically, the difference is in part 1, I focused on pretty easy trig equations. And by that, I mean there was only one trig function in each equation, because I really wanted us to focus on the concept of there being infinitely many solutions and knowing when to use that plus 2k pi notation. So today we are going to make them a little bit tougher. And we're going to look at equations that have more than one trig function in each equation. It might be two completely different functions like sine and cosine. It might be the same equation but powers. You might have a sine x and a sine squared x, things like that. When that happens, there's a little extra work at the beginning for you guys to do the isolation part. So one thing we're going to focus on for today is something we talked about in 10.1, and that's factoring equations that have trig functions. So I want you guys to remember something called the zero product property that you learned earlier. It says if two numbers, a times b equals 0, the only way that can happen is if one of them equals 0. And basically that's the concept behind solving by factoring. And the reason I bring this up, I want to remind you guys, if you're going to try to solve by factoring, you have to make sure the equation is equal to 0 first. If an equation is equal to something other than 0 and you factor it, you can't solve it that way. So let's start with this example right here. We're going to solve for theta, and I gave you the interval theta between 0 and 2 pi. So as a reminder from part 1, what that means is I'm telling you, number 1, I want you to answer in radians, because I said 2 pi and not 360 degrees. And number 2, don't worry about repeats. Just give me the answers from the unit circle and that'll be it. Now when I look at the equation itself, I notice a couple things. Number 1, it is equal to 0, which is good if I want to solve by factoring. And number 2, I have a common term, a cosine theta. So if you have a common term, let's go ahead and factor that out. So I'm going to factor out the cosine theta, and it's going to leave me with 1 minus 2 sine theta. And what you have, if you think about what we just talked about with the zero product property, is we have a times b equals 0. And that means we can separate them. So either the first part, cosine theta equals 0, or the second part, 1 minus 2 sine theta equals 0. Now the first one is already ready to solve. If cosine theta equals 0, then from the unit circle, theta could be pi over 2, or 3 pi over 2. Now the second one we need to isolate first. This becomes like a part 1 question. So what I would do is add 2 sine theta to both sides. And we get 1 equals 2 sine theta. Let's divide that 2 out of there to cancel that. And what we end up with is sine theta equals 1/2. So our other two answers are going to be the two places from the unit circle where sine equals 1/2. And that would be pi over 6 and 5 pi over 6. So we get 4 total answers. These 4 things here together are all the answer. All right. Now another thing we're going to do today is also from 10.1. We're going to use the trig identities we know to simplify these equations and make us able to solve them. Now one thing you might want to use this for is if you have completely different trig functions in your equation, it's always better to try and turn them into the same thing because that lets you factor. So let's do this for our second example. We're going to do 2 tangent squared x minus 2 equals secant squared x. And what I notice here is we have 2 completely different trig functions. We have tangent and secant, but they are squared. And every time you see a squared trig function, you should at least think about the Pythagorean identities. Now one of our Pythagorean identities says, and I'm going to recopy the first half of this, 2 tangent squared x minus 2. One of our Pythagorean identities says secant squared x equals 1 plus tangent squared x. And now what we have is the same trig function, which is what we wanted. And in fact, since they are exactly the same, let's just subtract tangent squared x from each side, cancel the one on the right. We get tangent squared x minus 2 equals 1. I would add 2 to both sides. We get tangent squared x equals 3. Take a square root. And what we have right now is tangent x equals, now remember what we have is a plus or minus, square root of 3. Don't forget your plus or minus every time you take a square root when solving an equation. Now here's the thing. Inverse tangents we talked about in chapter 9, they're a little bit tricky because when you're looking for square root of 3, you got to realize where it came from. Getting square root of 3 for tangent comes from having a radical 3 over 2 over a 1/2. Because that would simplify to be radical 3. So really what you're looking for is the place where sine is radical 3 over 2 and cosine is 1/2. Now on the unit circle, that would be pi over 3. That would be the first place it happens. Now remember in the directions, since I didn't specify, that means I do want radians, which we did. And I also want you to use that k pi notation. Now for tangent, we said you don't need to do plus 2k pi. You just pick one answer from the unit circle and do plus k pi. Now the second half of this question says, what if it was negative radical 3? What if tangent x is negative radical 3? Now that can happen when either one of these, sine or cosine, is negative. It actually doesn't matter which one you choose. Let's say it was the top one. Let's say I put a negative right there. So if I had negative radical 3 over 2 over positive 1/2, then tangent would be negative radical 3 here also. Now the place on the unit circle where that happens would be 5 pi over 3. That's where sine is negative radical 3 over 2 and cosine is positive 1/2. I put my plus k pi on the end, and those two expressions together are the answer to the question. All right, I want to do one more example with you guys. And for this example, we want to solve for theta again. We're going to do 0 to 2 pi again, so radians, unit circle only. And our equation is negative 1 minus cosine theta equals sine squared theta. So I have two completely different trig functions again, cosine and sine. But again, they are related by Pythagorean identities, and we have a sine squared there. So remember from your Pythagorean identities that sine squared theta is 1 minus cosine squared theta. So let's make that substitution. I'm going to leave the negative 1 minus cosine theta here, and I'm going to substitute 1 minus cosine squared theta here. So now I have all cosines, which is good. But one of them is just cosine theta, and one of them is cosine squared theta. So we need to group everything together and see. This is probably going to end up being factoring. Let's see what it looks like. So in order to group everything together, let's start by adding cosine squared theta to both sides. Cancel that out. So we'll have cosine squared theta minus cosine theta minus 1 equals positive 1. And then I subtract 1 from both sides, because I want to cancel out that 1. I want it equal to 0 to factor. And I get cosine squared theta minus cosine theta minus 2 equals 0. So now when you have this situation here, when you have one of your trig functions here squared, one of your trig functions here, the same one but not squared, and then a constant term here, we can factor that just like a quadratic, except instead of having x, you're factoring in terms of whatever is here. In this case, it's cosine theta. But the factoring part is the same. You're looking for two numbers that multiply together to negative 2 and add up to negative 1, and that would be negative 2 times positive 1. So that's how you factor a quadratic-like equation with trig functions. And we're going to finish it using the zero product property. So here's what we have from before. we're going to separate. We're going to say, okay, I have a times b equals 0, so either a equals 0 or b equals 0. Now we're going to solve each one. If I add 2 to both sides, I get cosine theta equals 2. So I'm asking myself, where does cosine theta equal 2? The answer is no solutions. For both sine and cosine, the biggest and smallest either one gets is 1 or negative 1. So if you ever have a cosine theta or a sine theta equal to 2 or 3 or 10, that's going to give you no solutions. Now the other one, if I subtract 1 from both sides, I actually am going to get an answer for it, because there is a place on the unit circle where cosine theta is negative 1, and that would be directly to the left, that would be pi. So I only get one answer this time, and it's theta equals pi.